New set of notes, today is the 13th. So it's a separate set of notes from the other ones that we just got done going back over. Trapezoids, we're gonna cover trapezoids. I'm gonna add a slide to this slideshow so that we can finish out the chart. So read that real quick so you got an idea why I shut it down.
You can freeze it and then add stuff back there. I can't. Oh, with yours you can?
One way the computer set it.
Oh.
Alright, so again, a trapezoid. Be able to use properties of a trapezoid, be able to give a quadrilateral the best possible name. This, after these, you're going to know all the quadrilaterals, so this chart over here will be finished. I'm getting ready to draw it. Again, you probably want to draw this somewhere in your notes. Probably the one that I'm going to draw on there will be the same thing. What happens here? A trapezoid. Here in the last year or so, they've changed this. It used to be that I put a trapezoid right here. Now, a lot of the math gurus are saying that instead of a trapezoid being its own branch out there off of quadrilaterals, it should actually go right there. So we should have done it before a parallelogram. And I'm going to show you why when we get to the definition here in a minute. Now in this chart, there's going to be another shape that we're going to put here, and there's going to be a shape that sort of comes off of a rhombus there. It's a rhombus and a square, but it's not a rectangle and it's not a parallelogram. So it's sort of, it's like a growth maybe that you have on the side of your head. It's not really anything. Right? Yeah, you got a growth on your head, don't you?
No.
You got a growth on, it's on your shoulders, I mean.
What's your head?
He looked to make sure that's the funny thing.
Listen to Derek, because she'll tell you.
What's your head?
I'm worried.
All right, so on this chart, again, draw this chart. You have quadrilaterals. You have quadrilaterals. What is a quadrilateral? Four sides. Off of quadrilateral, we had what? Parallelograms. Again, we want to hurry and get through this. What key idea about parallelograms? Both pairs of what?
Sides.
Opposite sides, parallel. Both pairs of opposite sides have to be parallel. Off a parallelogram, we had a branch that went to what? Rectangles. What was the key idea about a rectangle? 4 right angles. Off a parallelogram, we also had what else? Rhombus. 4 congruent sides. Then off of those two went together. We said it would be a what? Square. Good. It's got 4 congruent sides and 4 congruent right angles, or 4 congruent angles, right? If they're all 4 congruent, then they have to all be right angles. So again, make sure you got this chart in there so you can refer back to it at some point. Again, I usually put trapezoid right here. But now they've changed the definition of it by one word. And changing that one word sort of changed everything on it. Alright? So trapezoid should actually go right here. Anybody have a guess as to what the other shape coming off a trapezoid might be? Let's keep that guess in mind for here in a second.
That's what's on the wall.
Isosceles, isosceles trapezoid. Guess what an isosceles trapezoid is? What's an isosceles triangle? Two sides, a triangle with at least two sides congruent. Guess what an isosceles trapezoid is? Trapezoid with two congruent sides. The one that comes off a rhombus here. What is it? Kite. We won't deal with the kite a whole lot. It's sort of the, yeah, it's sort of a loner that really doesn't have a whole lot of properties, doesn't work out real well with all the other stuff. So that's our whole thing. Now, a trapezoid. The key thing for a trapezoid that we should write out here, and you'll write it out here in a second, is sort of like a parallelogram, except instead of both pairs of opposite sides being parallel, guess what has to happen? Instead of instead of both pairs, opposite sides being parallel, one pair of opposite sides are parallel. And I'm going to put the definition up here now. This is the definition of a trapezoid. The word that they left out now in the definition is this word. Instead of saying it has exactly one pair, now they're saying it has one pair. So what else could it have?
You could have, it actually could have two.
Could have two. And if it had two, we wouldn't call it a trapezoid, we would call it a parallelogram. So that's why trapezoid would go here. Then all parallelograms are trapezoids, but not all trapezoids are parallelograms. So that's all. They changed the definition by that one word. Got rid of that word, and now it sort of falls in a different spot, sort of. Still the same idea. And apparently, all other countries, I don't know about all other countries, but most other countries have always used this definition, and that's why the math people in the U.S. now are trying to sort of switch to that. I'm not sure why they're worried about a trapezoid and they're not worried about the metric system. Because I wish we were on the metric system. That'd make a whole lot more sense. All right, draw, not this one. I'm gonna go to the next one. Draw this trapezoid. Some of the stuff that I put up here, I'm gonna put a bunch of stuff up here and we're gonna label this trapezoid. Draw it big enough where you can put a bunch of stuff in it. So make sure, sorry, I probably should have said that first. Make sure you make it big enough where you can put a bunch of symbols and everything else in it. Still with us, Bryant? Still with us, Bryant? I heard you say, I didn't see you start moving it around like you were still with us. So. Oh, shit.
I didn't lose his name. Yeah, I think Brian's name.
This?
Yeah, Dad.
Remember last time, where did you see that?
It's out that door and sitting right there in the hallway.
Down in Mr. Fisher's office?
It could be there.
Is that what you want it to be? Because then I gotta write it up and call the house and go through a bunch of headache.
I don't
You don't care? If you don't care, I can stop this and we can take care of it.
If we could stop this.
Wait, we're stopping what, class?
For now, for the two.
Oh, if this is just temporary, then you might as well just go on.
We can make it permanent. I'll have a talk with him. So you think this is funny and I don't. I'm not laughing. Because if you're gonna, we could.
You can continue.
Thank you. I'm glad you allowed me to do that. The first thing, segment AD and segment BC. So on this, you should have labeled it. Again, you got to be moving quickly and you got to be writing stuff down as I'm doing it. Those two are called bases. Now normally, because when we had a triangle, we just had one base, right? So we don't get these bases mixed up.
Base one, base two.
We call them like base 1, base 2. Very good.
We did this last year.
Did you? So base 1, base 2. Those two are always parallel to each other. So put that in your drawing there. Again, some of this stuff up here, maybe you don't have to write it down because you're putting it in the drawing. Depends on which way is going to make it easier for you to remember when you refer back to it. Maybe you do need to write it down. Next thing, AB and DC are called the legs. So this is a leg. That's a leg. Just like in an isosceles triangle. What was this side down here at the bottom called?
Base.
It was called the base. What were these two sides called?
Base.
Legs. Does anybody remember what these angles right here were called? If I could ever hit them.
Vertex.
The other two.
Oh.
That's the vertex angle up top, right? Those two were called the base angles, and that's what these are called. Those are base angles. Those are base angles. We're going to talk about those on the next slide. Now I drew in this extra segment going across here, segment EF, because that's something special. What's it look like point E is there? Midpoint. I would write that right there. E is a midpoint. What's it look like F is? Midpoint. Now that segment is special. It connects the midpoints. Have we ever talked about a segment that connects a midpoint to something? When we were dealing with those triangles, which one connected a vertex to the midpoint? Which one connected the vertex to the midpoint?
That one. Oh, central.
Not centroid. What was these called? They were medians. Guess what this one's called? That segment running across through there. It's a median. That's what it says. It already popped up. So EF is a median. This you might want to make sure you write down. This is very important about a trapezoid. Connect the midpoints of the two legs. It's called a median. Now, give me one thing that looks like it's true about segment EF, that median.
180.
So I guess. Give me something else. What can you tell about the two bases in it?
They're parallel.
They're all parallel, so you might want to put another parallel. All three of those are parallel. That's one of the things I'm going to say here in a minute. The other part. Median's always parallel to the bases, and its length is equal to 1/2 the sum of the bases. I'm going to write this equation down up here. I highly suggest that you write this equation down for this next to this one.
Isn't it base one plus base two divided by two?
Now, it's not because of what you're thinking, but yes, it is. The median equals base 1 plus base 2 divided by 2. So if you're looking for the length of the median, you can find it just using that. So let's do this. If I told you base 1 up here was 25 centimeters, base 2 was 15 centimeters, could you find the length of that median? 20? How'd you get that?
You add together and then
25 plus 15 is 40. Divide that by 2, you end up with 20. All right? What should always be true about the median in relationship to two bases?
it should be parallel.
That's true, but what about the length of it? Should be in between them, shouldn't it?
Yeah.
So if one of these is 15, one's 25, the base has got to be somewhere in between 15 and 25. So if you came up with the median being 70, you know something's wrong. All right? What if I did this? Let's get rid of those two. We'll leave that one 15. What if I told you the median here was 18 centimeters?
You can figure it out.
Could you find the base?
Yeah.
How would you go about doing that?
You have to put base 2 in there, and you kind of put median in there.
All right, so you could use the formula and use it backwards, right? What's median?
18,
18 equals, what's base 1?
X, question mark,
Question mark or x plus what?
15,
15 divided by 2.
times 2 both sides.
Times both sides by 2, then do what?
Minus 15.
Minus 15. Now, if you do a couple of these, instead of doing that every time, you might find it easier to go in here and take the median, multiply it by 2, and then just subtract off the other base, and whatever's left is the base that you're missing. What is it? Let's try it up here. What's 2 times 18? 36. X plus 15, what do I do there? Subtract 15.
21.
What's x? So that side would be, that base would be 21. So make sure you got that formula down. Next, just write this down. That's all you gotta write down. Isosceles trapezoid, and draw that picture real quick. We're gonna label some stuff on it. So this is an isosceles trapezoid instead of just a trapezoid. And I probably should have said this on the other slide, because every trapezoid I've had up here has all looked the same, haven't they?
Yeah.
This is another way a trapezoid could look,
It's like half a trapezoid.
where these two sides are parallel. This is another way a trapezoid could look. Alright? So don't get stuck. As long as they have one set of parallel sides, it's a trapezoid. Don't get stuck thinking every trapezoid has to look like the ones that I put in here. The only reason I put those in here is because that's what the computer will draw for me. Alright? An isosceles, so not every one is an isosceles trapezoid. On this isosceles trapezoid, a few things. Number one, the legs have to be congruent, so mark those congruent. What do you still know about the bases? They're parallel. Now, in an isosceles trapezoid, what looks to be true about these two angles? They're congruent to each other. Those base angles are congruent. Guess what's true about these other two base angles? They're congruent. So we know all that about an isosceles trapezoid. There's actually a little more here. Oops. Hit the wrong, I hit the wrong thing. Did everybody get that before I erased it?
Yeah.
So we know these two are congruent. We know these two are parallel. We know these two angles are congruent. We know these two angles are congruent.
Do you mind while you're talking, I will freaking
Do what?
go up my thing and work. My thingy.
If I draw in the diagonals, my diagonals might not be drawn real well. Do the diagonals bisect each other? Is the distance from here to there the same as the distance from here to there? No, so unlike a parallelogram, diagonals don't bisect each other. But what looks to be true about these two? They're the same. What looks to be true about these two? They're the same. What's true about these two angles right here? They're the same also. So that angle's congruent to that angle. What kind of triangle is this triangle right here on the top? Isosceles, good. What kind of triangle is this triangle on the bottom? So what do you know about these two angles then? They're congruent. Alright, now does that mean, do we know everything else? Do we know that this angle is congruent to this angle? No. The other thing that we do know, these angles that are consecutive angles, sort of like a parallelogram, guess what has to be true about them? They add up to 180 degrees. You might want to make sure you write that down. That's sort of important about a trapezoid. That works for all trapezoids, not just an isosceles trapezoid. These angles add up to 180. Guess what's true about these two angles? Add up to 180. Now, does that mean that this one and this one are going to add up to 180? No, it's just a lower base angle and an upper base angle. So lots of stuff there. Last thing. Oops, that's not what I wanted. This just says what we just wrote down there. Isosceles trapezoid have base angles that are congruent. Diagonals, they don't bisect each other, but they are congruent to each other and they split each other up sort of the same. The last thing, a kite. This is the definition of a kite. Quadrilateral. With two pairs of disjoint, now you don't know that word, but disjoint congruent sides. I'm going to explain it.
Two parts or
Two pairs. If I draw this picture, man, it's not getting right. If I draw that picture, and these two sides are congruent, and these two are congruent. What it means by disjoint. If I was to cut this kite right through there, I have two congruent sides here and two congruent sides here.
Good afternoon, everybody. Time for a couple of
Does that work with a parallelogram?
First
No.
of all, good luck tonight.
Alright, so that's a
Our
kite.
softball team, as they will have a home game tonight versus Centerville, Indiana, here at 5 o'clock.
That was a
Our
question.
JV baseball team, as they will travel to Franklin Monroe for a 5 o'clock game. We also want to wish congratulations to our varsity baseball team, who are now 3-0. They defeated Seton Catholic in 6 innings, 11-1. Charlie Watts.
This is the other part of the assignment.
Go Blazers.
Make sure you do
Next
both
home game
parts.
will be tomorrow for our varsity at 5 o'clock versus Ansonia.
It will be collected next time, so make sure you write that down. 434 and 442.
Rest of your Monday. We'll
Finish
see you back here tomorrow. Thanks a
434,
lot.
do 442. Both parts. We got what, 10 problems done of the other one, so there should be about 20, 22 or something like that total problem. 21, I don't know, something like that.
So do you have a ring? Or it could be fully one.
That assignment will be collected next time.